Here is our project about bang bang thrusters for Aero 421, presented by Kate, George, Rayson, Riley, Cassandra, and Grady.
So you may be wondering, what is a bang bang thruster? It is a thruster that has two discrete states, no thrust and full thrust. These kinds of thrusters are most often used for altitude and control purposes to orient the spacecraft correctly, but can also be used for larger orbital maneuvers with larger, more powerful thrusters. To use bang bang thrusters effectively, they are set up in arrays and clusters to optimize control in all axes. On the right, you can see an example of bang bang thrusters. Those are two of the four RCS quad thrusters on the Apollo lunar module. They were used to manually orient the spacecraft upon landing on the moon.
Bang bang thrusters receive their name from their binary use. Thrusters are toggled abruptly between completely on or completely off. In practical engineering applications, these thrusters are controlled by solenoid isolation valves. Rather than supply a specific thrust value, the cycling of these valves at specific frequencies allows the spacecraft to achieve a desired torque. This can be seen in the plot depicted, where thrusters in opposite directions are varied between no thrust and maximum thrust at varying frequencies.
Bang bang control thrusters first saw use in the 1940s, starting with missiles developed during World War II. It wasn't until the 1960s that they see use in spacecraft, however, starting with the Gemini. The Gemini used the thrusters to control its attitude. A few decades later, similarly to the Gemini, the Space Shuttle also used bang bang control thrusters to control its attitude, this time being with a group on the front and the back of the spacecraft. While not a spacecraft, Lockheed Martin's experimental multiple kill vehicle, abbreviated MKV, was a small craft designed to intercept incoming missiles. It used bang bang control thrusters to control its altitude and attitude. In the video of the firing, you can clearly see the behavior of the bang bang thrusters, as they are either fully on or fully off. One of the more current uses for bang bang control thrusters is on the Orion spacecraft, which is currently being used for the Artemis missions. However, the Orion also makes use of PID control, not just bang bang thrusters, for its RCS.
If bang bang thrusters are only off and on, how would you get continuous thrust? Although they are discrete thrusters, they can be used to simulate different levels of continuous thrust. First, clustered configurations. When set up in clusters or arrays, the thrusters can be fired in sequence to approximate continuous thrust. Secondly, using pulse width modulation, the thruster firings can be modulated to simulate continuous thrust by adjusting the duty cycle. In other words, by adjusting the pulse duration and the interval between pulses, the average thrust can be controlled to create the desired level of continuous thrust. If you wanted the thrust to be more continuous, you would increase the frequency, duty cycle, and amplitude of the firings.
Pulse width modulation, or PWM, and pulse frequency are simple yet effective techniques used to achieve precise control over spacecraft thrusters. PWM enables the use of digital means to obtain analog results. When digitally controlling thruster firing, a square wave signal is generated, which is either on or off. By manipulating the width and frequency of these pulses, the thruster can be activated for specific periods of time, allowing for fine-grained control over thrust production and creating a more continuous torque profile. In essence, PWM empowers users to achieve any desired control torque, rather than being limited to the maximum torque. PWM finds applications in various control systems, including servos, telecommunications, and voltage regulation. In this type of control, a measurement is taken at each sample period, and a control torque is calculated accordingly. In Figure 4, the solid line TC represents the commanded control torque over time. On the other hand, the dotted line TT illustrates the torque produced by the thruster during firing. An equation is employed to determine the duration of each pulse, considering TC of Tk as the commanded control torque at time Tk and delta T as the time between samples. By employing this method, the average torque exerted throughout the sample period aligns with the average commanded control torque.
The number of thrusters a spacecraft needs is entirely dependent on the mission goals and requirements that are set for the spacecraft. In order to control attitude with a bang-bang thruster system, a minimum of 3 thruster pairs are needed for the full 3-axis control system. Since a single thruster is generally not bidirectional, an opposing thruster is usually needed. Also, due to the nature of imparting a force rather than a pure torque, 6 pairs are generally used to have a pure attitude control. This gives us around 12 single directional bang-bang thrusters to have pure attitude control. For a thrusting configuration rather than attitude control, larger single directional thrusters are put in place generally in line with the center of gravity, and the number of delta V thrusters needed will also entirely depend on requirements. There are 2 forms of thruster layouts. Propulsive is for changes in spacecraft velocity, features thrust vector collinear with center of gravity and larger thrust values, and RTS is for changes in spacecraft attitude, features smaller thrusters generally offset from CG to impart a moment or a torque. Some axes of rotation may need more control authority dependent on mission requirements. This would lead to a larger or more pronounced thruster vector concentration. Generally, in spacecraft, thrusters are laid out with controllability that gives freedom of attitude adjustment in all 3 axes of rotation with respect to the center of gravity. Bang-bang solenoids are prone to failing often due to their high cycle time and overall stress demands, hence redundancy is critical. A minimum of 6 thrusters are required for full control 3 axes with both directions. Generally, thrusters are paired or have a symmetric counterpart to be able to maintain full control under a single thruster failure. Less mission-critical RCS systems may not need to provide redundancy due to a variety of factors, some being confidence in system, i.e. low risk, cost, complexity, weight, etc. All these factors come down to risk assessment and requirements.
The firing selection process is an autonomous cycle that starts with onboard sensors like gyroscopes, star trackers, and accelerometers that send current attitude information into a closed-loop control algorithm that calculates the error to the required attitude. After calculating the target error, the control algorithm determines which thrusters to fire, for how long, and at what intervals. The control then sends the fire command. A unique component of bang-bang thruster algorithm is that while the thrusters are firing, the algorithm is continuously calculating the error between the current and target attitude and adjusting the firing pattern. This is known as closed-loop feedback control. The loop is illustrated in this basic Simulink layout in which, given a reference angle, the error is calculated and provides a command torque to achieve the desired attitude. The simulation was run and the results are seen in the video.
While bang-bang thrusters are extremely useful for spacecraft attitude and control, there are several drawbacks and limitations that must be considered. In theory, these systems are extremely efficient, but in reality, hardware limits its capabilities. Frequent cycling, especially over long-duration missions, can lead to mechanical failure of the system, most commonly occurring in the solenoid isolation valves. Additionally, these valves can only actuate at a maximum speed, which limits the duty cycle and ultimately the torque that can be achieved by the system. Finally, it is important to note that these thrusters have a non-zero rise time to achieve max thrust. In theory, we assume this time to be 0, but in reality, the system must wait until the thruster reaches max performance before toggling to off. This concept also limits the duty cycle and maximum torque.
Mars 2020 is one of the missions that use bang-bang thrusters, especially on the Sky Cream rover coming down. Artemis as well is one of the other missions that has used bang-bang thrusters. The Orion spacecraft used it during re-entry. And CubeSats tend to use bang-bang thrusters for their ADCS as well, in the forms of Rousseau jets and other micropropulsive devices, and NASA Safer. The jetpack also used bang-bang thrusters to control attitude.
Provided here are the references we used in research of this project. Thank you so much for your time, and we hope that you enjoyed learning about bang-bang thrusters.